Higher Notes, Unit 1, Section 5, Gravitation. And this is Part 1, Projectile Motion. Well, a recap, first of all, on what exactly projectiles are. And you may remember back in 4th year where we took two ball bearings. I'll shade one black to distinguish it from the other. And they both started off at the same height. And if the ground were here, let's imagine that the white ball bearing was allowed simply to fall under gravity. Well, it would fall straight down like that, and its acceleration would be uniform and would be g, which is 9.8 meters seconds to the minus 2. So that's the white ball bearing. The black one is projected horizontally, let's say. And of course, as I'm sure you know, its motion is like this. It follows a parabolic path. Parabolic trajectory. Interestingly, they both take the same time to hit the ground. So let's imagine the first ball bearing took 0.1 seconds to hit the ground. The other one would take exactly the same. So what's going on there? Well, in the vertical, let's look at the black one at various positions in its flight. Well, in the vertical, the black ball bearing is falling under gravity, and its velocity gradually increases at 9.8 meters per second per second. So the acceleration in the vertical here is an acceleration which is g, which is 9.8. Okay, obviously the sign convention in problems would require you to take that as minus 9.8, so let's put the minus in, and I suppose we should put it in for that one as well. So the main point is that in the vertical, both ball bearings accelerate at 9.8. Even although in the horizontal, there's a uniform velocity, Vx, let's say, which doesn't change throughout the motion. So whereas in the vertical we've got an acceleration for the parabolic path, in the horizontal we've got a constant velocity. And it's this combination of the uniform velocity in the horizontal, Vx, combined with the uniform acceleration in the vertical, 9.8 going downwards, that produces the parabolic path of the projectile. And you're quite familiar with all of that from National 5. Well, you certainly should be. And of course we neglect air resistance throughout all of these problems. Now the difference at higher is that you're going to get problems where it's not a horizontal launch but an angled launch. So here's the new higher projectiles approach. Right, so what are we going to be dealing with here? Well, we're still going to have the ground. But we're going to have like a kind of golf shot type scenario where the ball is launched up at some angle and then it comes back down again. That should be a nice symmetrical parabola. In the horizontal case, in fact, you only had 1/2 of the parabola. It was as if you were starting at the top of the flight, whereas here at higher, we're dealing with the full parabola. Now at launch, the projectile, let's say it's a golf shot, will leave the ground with a certain velocity v. Let's imagine, well, let's give it its initial velocity u. So let's give it that, and let's make it 40 meters per second, let's say. And it will also be at an angle to the ground, theta. Let's make theta 25 degrees here. Okay. So that's the sort of scenario that you will get. Now, there's always some hidden information in these problems. At the top of the flight, the vertical velocity Vy will be 0. Only in the vertical. Obviously, the horizontal component is still non-zero. It's still present. But it's always worth bearing in mind that top of the flight scenario. And the time of flight will be t for the whole flight. So, usually before you can do anything in these problems, you've got to get the horizontal and the vertical components of the velocity worked out. Okay, so I'm not going to derive these, but you should know that ux will always be u cos theta, and uy will always be u sine theta. If you're not sure where that comes from, you should look up your jotter for an explanation. You should be able to work it out. So, in this particular case, ux then is going to be 40 times the cosine of 25. So the horizontal velocity at launch will be 40 times cos 25, which equals 36.3 meters per second. So the horizontal component of the velocity is obviously less than the launch velocity, because the launch velocity contains the horizontal and the vertical components combined. And this horizontal velocity at launch is constant throughout the whole of the motion. So once you know that horizontal velocity, ux, it is unchanged throughout the whole of the motion. Now, it's always a good idea to put the words horizontal in above your horizontal working and vertical above your vertical working. And because they both occur independently of each other, it's wise to keep them separate. Don't get them mixed up. So that's the horizontal velocity. Let's get the vertical component at launch. So it will be 40 times the sine of 25. Let's see what that is. 40 times sine 25. And that's an initial vertical velocity of 16.9 meters per second. Now that's the launch velocity in the vertical. Obviously, as the projectile rises higher to its maximum height, it eventually reaches a vertical velocity of 0, so it's decelerating on the way up at minus 9.8 meters seconds to minus 2, and then of course it accelerates in the vertical on the way back down. And when it comes back down to the ground, by symmetry, its final vertical velocity will also be 16.9, but downwards, so that would be minus 16.9. Okay. So we've now got the horizontal velocity worked out, and we've got the initial vertical velocity worked out. So typically, what might you be asked to find? Right, well, let's try a few things. So find the time of flight. Okay. Now, this is essentially got to be a vertical problem here, because although we know the horizontal velocity, we don't know the horizontal distance, that's the horizontal range. So there's no point in trying a horizontal bit of working here. It's very much a vertical one. So we write the word vertical. And now we've got to decide, are we going to work with the whole motion, or just the first half, or just the second half? And in this case, it's as well just to work with the whole motion. So I'm going to say that. And you need to always specify whether it's horizontal or vertical, and whether it's the first half or the second half or the whole motion. You then, because it's an accelerating situation, in the vertical it's always an acceleration, of course, list uvast. Now, you don't always need to write these little y's in, but I'm putting them in for emphasis because it's the y direction. Well, uy initially is 16.9. Now, I'm dealing with the whole motion, and a hidden bit of information is that by symmetry, if I'm launched vertically at 16.9, then I'm going to return vertically at minus 16.9, so I can actually put in minus 16.9 in there. That's a hidden bit of information. The second hidden bit of information is the acceleration due to gravity, which of course you should know. And the third thing you can put in simply by treating the whole motion is that because the body returns to the ground, then its vertical displacement is 0. So you've got those 3 bits of information there simply by knowing the physics of the situation. You've then got to decide how I get the time of flight. So you need to choose an equation which involves t, obviously. So it's either a is v minus u over t, or it's s is ut plus half at squared. Either of them will work. I'm going to go for a is v minus u over t, because t is my only unknown. So minus 9.8 equals, now watch your signs here, minus 16.9 is v, minus 16.9 again, divided by t. Okay. Well, rearranging the algebra tells me that minus 16.9 minus 16.9 is minus 33.8. So that's minus 33.8 divided by the minus 9.8. And that gives me a time of 3.5 seconds. To two significant, oh actually hang on, 3.4 seconds to two significant figures. Let's watch the rounding there. So, there we have it. No, hang on. Yeah, 3.4 seconds. So there we are. There is the time of flight for the whole motion. What else might you be asked? Well, you might be asked, what's the greatest height reached? So find the greatest height reached. Well, I hope it's pretty obvious that that is a vertical problem. But because we're going to the greatest height, it's the first half of the motion. And you should write vertical, and you should write first half of motion. Now, because the variables are different from part A, I need to relist my UVAST, because they're not the same as before, because I'm only going halfway this time. Again, this is all in the y direction. Well, my initial horizontal velocity, vertical velocity, sorry, is still 16.9. Now, the hidden information here is that the final vertical velocity is 0, because at the top of the flight, Vy is 0. So I put that in. A is another hidden bit of information, minus 9.8 meters seconds to the minus 2. This is what I'm looking for. Because I now know the time of flight is 3.4, then I can easily just say, well, half of that is the time to the top of the flight if I needed to use it. But I can get away without needing to do any intermediate rounding of the time there by just saying that v squared equals u squared plus 2as. So I can say then that 0 is 16.9 all squared plus 2 into minus 9.8, don't forget that minus sign, times whatever s is. Right, so let's take the square bracketed term over to the left, so 2 times minus 9.8 is 19.6. So 19.6 times s is equal to 16.9 all squared. Well, I'm actually just going to leave that 16.9 squared to avoid intermediate rounding. And this is exact, so that's okay, so over 19.6. So that then gives me 16.9x squared divided by 19.6, and I get 14.6 meters. Always answer the question though. The golf ball, I think we said it was a golf ball, didn't we? So the ball reaches a maximum height of 14.6 meters. So just make it absolutely clear that you realise that is the greatest height reached. Okay, so there we are, the height reached. What else might you be asked to do? You might be asked, what is the horizontal range? Or how far did the golf ball travel in the horizontal? Well, by its nature, that's a horizontal problem. And in the horizontal, of course, all we're dealing with are three variables. And if it's the horizontal range, we're dealing with the whole motion. So you can see I'm showing the reader of my solution, the marker, that I know this is a horizontal problem and I know it's the whole motion I'm dealing with. Well, right back at the beginning, we got the horizontal velocity 36.3. That's uniform throughout. There's my unknown. And my time of flight I got earlier, 3.4 seconds for the whole motion. So ux is sx over t. That's just the simple velocity equation. So 36.3 equals sx over 3.4. 3.4 times 36.3. So 36.3 times 3.4, and I get 100 at 23 meters for this particular shot. So that's the horizontal range. Right, that's part C. It's also quite common to be asked basically what is the kind of final velocity. I suppose that would be quite straightforward actually, because it's really just going to be whatever the initial one is at the same angle. So I don't think we need to go into that. If you were asked what's the resultant velocity just before hitting the ground, you could just look at the scenario here and say, well, it's 40 meters per second at 25 degrees above the horizontal, so I don't think there's any need to work that one out. Right, well, there we are. So those are the sorts of approaches you would need when dealing with an angled launch projectile. And all I'll say for part D is, well, let's ask the question anyway. What is the velocity of the ball just before landing? Well, notice when we say the velocity, what that means is resultant velocity. In other words, the horizontal and the vertical combined. Well, going back to our diagram, you saw earlier that it was launched at 40. I said that in the question at 25. And what I'm saying here is that it comes back down by symmetry at 40 meters per second as well. And it must also be at 25 degrees, and that's by symmetry. Okay, and just to so we can let's write the answer to that, I suppose. So by symmetry, 40 meters per second at, what did we say it was, 25 degrees? Yep, at 25 degrees above the horizontal. That's the way to phrase it. 40 meters per second at 25 degrees above the horizontal. And just before we leave this problem, if we go back to the original diagram, you can see the initial launch velocity. Let's just put in the components to show you how they add up. So if we were to put in our horizontal component of velocity, it would go along to there. That would be our 36.3 meters per second. And our vertical component, let's make it purple, would be that one, so that when you add them tip to tail, that's your 16.9. So your 36.3 meters per second added tip to tail to your 16.9 gives you your initial 40 meters per second launch velocity, and that's the same kind of vector diagram as you'd have at the very end, except the 16.9 is now going down the way. So that's how you work out problems involving angled launch projectiles.